Greetings, Chem students! My name's Ryan, and in this video I'm going to tell you all about the lab measurements experiment. Let's start by talking about what the point of this experiment is. Your goals in this lab are 1. To identify a metal, and 2. To determine the concentration of an unknown salt solution. Also, as you take the measurements you need to accomplish these things, you'll develop a couple of skills that will help you out in other labs. One of these skills is the fine art of taking measurements and reading glassware. As we'll see, there's a bit more to doing this than you might think. The other thing you'll learn about is how to properly use 4 different pieces of lab glassware. These pieces are the graduated cylinder, the burette, the volumetric flask, and the pipette. Now let's see how the unknown metals part of this lab works. Like I said a minute ago, your goal here is to take one of these slugs and figure out what kind of metal it's made of, which you'll do by determining its density. In other words, its mass per unit volume, or to put that another way, how much it weighs for its size. Once you have the metal's density, you can use a list like this one to tell you what kind of metal it is. To get your slug's density, you're going to need 2 different pieces of information, the slug's mass and its volume. You can calculate density from these by dividing the former by the latter. Getting the slug's mass will be easy. All you have to do is weigh it on a scale. The volume, however, will be a bit trickier. With the tools you have available in lab, the best, most precise way to get the slug's volume will be water displacement. To do this, you'll measure the amount of water you place into a graduated cylinder, slide the slug in, and then remeasure the water. The idea being the difference in water measurements will be equal to the slug's volume. Like I mentioned earlier, there's a little more to taking these readings than you might think. See, there's a certain technique you need to employ to read graduated glassware properly, and that technique is interpolation. To show you how this works, I've got a graduated cylinder here with some water in it, and you can see the bottom of the meniscus, that's the curvy shape the top of the water takes, the bottom of the meniscus falls somewhere between the 27 and 28 milliliter marks. To read this properly, we will use our imagination to divide the space between these markings into 10 segments, and see which of these imaginary lines the meniscus's bottom lines up best with. In this case, it seems to line up best with the 27.5 mil marking, so we would read and record this as 27.5 mil. If you're trying to read a piece of glassware you've never seen and you're not sure what you're supposed to interpolate to, just take the actual physical markings on the piece you're working with and divide by 10. This graduated cylinder's markings go up in increments of 2 milliliters, so you would read and record this one to the nearest 0.2 mil. If you've never done this before, it can sometimes be a little hard to figure out what the value of that last digit is, especially since the lines I put up on the example cylinder don't really exist. Just do the best you can, and don't worry too much if you read a little high or a little low. Interpolation is, after all, subject to interpretation. Now let's move on to the second part of your procedure, where you'll determine the concentration of an unknown salt solution. This part is similar to the first in that you'll do this by taking a sample of the solution and measuring that sample's mass and volume so you can calculate its density. But what does a solution's density have to do with its concentration? Well, it turns out, if you take a beaker of water and start adding salt or sugar or some other solute to it to make a solution, that solution's density will increase as the solution's concentration increases. Therefore, if you knew what the math relationship was between the solution's density and its concentration, you could use that to determine concentration from density. Here's an example of a graph that shows the relationship between a sugar solution's density and its concentration. As you can see from the best fit line, as the one goes up, so does the other. It also has the equation for the best fit line right here. So, if we had an unknown sugar solution with a density of 1.22 grams per mil, to get that solution's concentration, all we'd have to do is plug the density in here and solve for x, which in this case is 1.73 moles per liter. Of course, in order for this to work, you'll need to know what the math relationship is between your salt solution's density and its concentration. To get it, you will have to make a few salt solutions of different concentration, measure the solution's densities, and plot density versus concentration. And this brings us to the second piece of glassware you'll learn about in this lab, the volumetric flask. To make a salt solution in a volumetric flask, you first put some salt into your weighing bottle, There'll be a diagram of some kind up on the hood to let you know how much salt, weigh the bottle, dump the salt out into a beaker, and reweigh the bottle. In your calculations, you can use the difference between weighings to figure out how much salt you took. Next, dissolve the salt in some water, transfer this to your flask, and get the remainder of the solution out of the beaker by rinsing it into the flask. Finally, fill the flask to its index line and invert it somewhere between 20 and 30 times to get the solution inside all good and mixed. Now that you have your first solution, you'll need to measure its density. To do this, you'll use a pipette to dispense a portion of it into a weighing bottle and weigh the bottle before and after. To use your pipette, you first use a pump to draw solution up to just past its index line. You then take the pump off and use your thumb or finger to hold the liquid up. Then let it drain down to the line and let it gravity drain into your weighing bottle. If you look close, you'll see a small bit of solution will get left behind in the pipette. It's calibrated to account for this, and this is why you don't want to use the pump to force the liquid out of it. So that's how you make and measure your first solution, but like I said earlier, to make a graph of density and concentration, you need to make and measure multiple solutions of different concentration. To get these, you'll need to dilute the first solution you made, which brings us to the last piece of glassware you'll get to know, the burette. To use a burette, you first fill it to somewhere past the 0.00 mil mark and drain a little of the solution out, enough to get it below the 0.00 mil mark. Now, there are two reasons for doing this. One, it gets all the air out of the spout at the bottom. The other reason is because it is hard, and time-consuming, to get the meniscus down to exactly 0.00, to the point that, for all intents and purposes, it doesn't happen. So, if you are truly reading the meniscus properly, you won't have any 0.00 milliliter readings. The next thing is to take an initial reading. Since the burette's physical markings go up in increments of 0.1 mil, you'll read to the nearest 0.01 mil, in other words to the hundredths place, by interpolation. If you're using a burette to dispense a certain quantity of solution, like you are in this experiment, you add the initial reading to the amount you want to dispense and let it drain down to about that level, give or take half a mil or so. You then take a final reading, again to the hundredths place. You can calculate the volume dispensed by subtracting the initial reading from the final. In this experiment, you will use burettes in this way to add various amounts of your salt solution to other amounts of water, which is how you'll get the diluted solutions you need to make your graph. After you've added the salt and water solutions together, make sure they're thoroughly mixed, and measure the mass of a portion of them the same way you did this for the first solution. Oh, and after you're done measuring the salt solutions you made, make sure to also measure out and weigh a portion of unknown, which is something you're gonna have to do if you want to calculate its concentration. Just one more thing before you go. The salt solutions you'll be working with will make your glassware all crusty if you don't get rid of it, and if that happens, you might lose neatness points from your lab. Just make sure you dispense of leftover solution in the lab room's waste container, and fill and drain each glassware piece you used with DI water to get the residue out.